5-10 minutes at the end of the presentation for discussion.
Yes.
But in case there are really urgent questions during the presentation, you can just reserve in the chat. You can just write in the chat that you want to ask something, and I will let you do. Sorry, Laszlo, for the interruption, please.
Yeah, and encourage everybody to ask short questions during my talk and to postpone discussions till the end. We'll have, I think, 5 to 10 or 15 minutes for this general discussion. So, my talk is about an activity of more than a decade conducted in collaboration with many people, started in Calabria. And I'll speak a little bit about history, make introduction so that everybody understands what's it about. And also, I'd like to stress that I see that my future co-authors, Rainer Schicke, Istvan Sonyi, and Sasha Skorinok, are online, and we shall profit, I hope, use this seminar also to discuss our present internal physical problems. We are now working, and we hope to finish it with a paper. I'll speak about mostly about general problems and leave details, for example, values of parameters, fits, and so on, to the end, which are less important. It's important that we understand and agree about the concept. So do you hear me? Yeah, you do. Yes.
Yes, please.
Yeah, this is the plan. I start with elastic scattering, and the subject is single, double, and central discussion with emphasis on resonance production, Regge factorization, direct importance of direct channel nonlinear complex trajectory, production of meson resonances, a new, relatively new and fashionable subject, glue balls and oddballs. Oddballs comes from the word oderon. Baryon resonances in single and double diffraction dissociation, and all together should be a coherent picture shown here. So here are the diagrams in question. This is elastic, obvious. These are two diagrams, single and double diffraction, when the proton gets excited diffractively. Diffractively, it means that there is a rapidity gap or a Pomeroy exchange between the two vertices. And then central diffraction, which means that in the central region, here, here, or here, we can produce meson states. Why mesons? Since two pomerons interacting can produce only a meson, and meson can be an F meson or an intriguing oddball glue ball. Now, this process at the center is surrounded, can be surrounded either by elastic vertices up and down, or also by diffraction dissociation, single or double. The relevant processes are shown here, and people who were involved and with whom I start are certainly Dino Goulianos, a paper written with Robert Ciesielski. These are the main papers. Now, the machinery, the tools, this is Regge. And the Regge in this context is like a toy, a Lego toy. One can combine by Regge factorization vertices like these, elastic or inelastic, and combine with propagators. Building the final goal is to have a scattering amplitude or cross sections. And there are many problems, big and small. I shall discuss it, and what my goal is that we understand each other, also with my future co-authors in this work. So I repeat that we started many years ago, and behind us were the names. So here are our papers. This is the first cycle of about 5, 6, 7 years of activity with Schicker, with Rainer Schicker and others. And this is the last paper in which we studied central production of glue balls. So here are the formula. The formalism comes from Engelmann, Schlein, Jaroszkiewicz, Lanzov, and Goulianos. And the essence is that a proton interacting with another one emits, radiates a Regge-Po trajectory, a Pomeron in this case, and this can be described by the total cross-section shown here in these brackets. This is a smooth Regge-behaved function, and it excludes resonance production. That is very important. So here are the denotations. They are more or less familiar. Here is the linear Regge trajectories that is exchanged in the P channel. And the first complicated, important point is to know that the trajectories, it's very important, are not linear. And there are two strict constraints. One is the threshold behavior. This is rigorous by Barot and Zwanziger many years ago. Near the threshold, the imaginary part of the trajectory must behave in this way, where T naught is the lightest threshold in the given channel. In our case, that is 4m pi, 2 pion threshold. So this is a particular number. So this is the value of the trajectory at the threshold. So the power is fixed, and it is, unfortunately, is not square root, while the asymptotics is square root. This is also rigorous. Clear, easy, the trajectory complex function cannot rise faster than a square root. So these are two constraints. Within these two constraints, one has to construct nonlinear complex trajectories. And here is a solution. I like the solution since it's very simple. Here it is. You see, yes? So this is the solution where we have the threshold, and we have, I come back, and we have a square root asymptotic behavior, and we have the necessary slope and intercept of the trajectory. So this is very simple. Unfortunately, the threshold is limited, is restricted by the mass of the mass of particles at the lowest threshold. So to reconcile it with the threshold behavior, with the asymptotic square root behavior is not easy. Now, on the other hand, trajectories in 90% of papers, even more, are assumed to be linear. And the reason for that is twofold. One is that the known meson resonances lie on linear Regge trajectories. That is, the real part of the trajectory against the squared mass is a linear function. Here it is. The other one is the Veneziano model, which was very popular, also valid only for linear trajectories. This is related with the string models and so on. So there is a strong belief that one should use linear trajectory, which is wrong, since the trajectory is a complex function and analyticity, unitarity constrains its behavior. So a realistic trajectory should behave like this. The real part rises, stops at some value. There are no more resonances with higher spins, while the imaginary part increases. So the qualitative behavior of the trajectory. Here it is. I repeat, the real part stops at some values of mass, of spin against mass. The real part of the trajectory is spin. And it stops to, it's about 3 g square, 3. And the imaginary part, the width of the resonances increases. So at some values of spin and mass, the resonances disappear. With Francesco Paccanoni, Alessandro Papa, and Roberto Fiore, we have working on nonlinear trajectories by using dispersion relations, starting from a almost linear behavior at low values of the argument, and then calculating in this rather complicated wave analytically the behavior of the real and imaginary part at higher values of the trajectory. Now, I come to the essence of this activity. Maybe I start with this one. In recent 10 years, 20 years, starting with the HERA data, experimentalists and theorists, BFKL, HERA, DAISY, all were studying the behavior of the structure function as function of X. And the structure function rises, these for various fixed values of Q square. The structure function rises, this is X, the horizontal axis is in X, the Bjorkin variable. And the smaller the value of X, the steeper is the rise of the trajectory. So everybody was looking for the smooth asymptotic behavior, discussing saturation, how fast, how long will this rise continue, and whether it can be described by BFKL formula of quantum chromodynamics. People forgot that at low values of X, at large values, like X close to 1, there are resonances. And the data from the class collaboration at Jefferson Laboratory, I come back, show that there are many resonances at X close to 1. So this is 0.4, 0.6, and 1. The previous transparency, here it is, implies values of X much, much lower, where the behavior of the structure function, this is a structure function, rises smoothly and steeply, while at values close to 1, the structure function shows resonances. And this is a very non-trivial thing. Now, this was noticed and quoted by Wolfgang Schäfer, who combined both the smooth asymptotic behavior, here it is, with the resonances, quoting our fits with Fiore, Flacchi, Lengi, Almagas in a paper called Kinematic Complete Analysis of the Class Data, published in 2004. The preprint is of 2003. Those times we were in the old building of the Calabria University. And the point is how to combine the smooth low X behavior with the behavior of the structure function with resonances. So that's the point. In hadron-hadron scattering, proton-proton in this case, diffraction dissociation was studied at Fermilab, and there were prominent, huge resonances in the missing mass. This is missing mass, and the horizontal line is missing mass, and it's very close. It's similar to the behavior of the tau cross sections. This is another experimental plot now from the LHC in the central region, where one sees also resonances not as clean as in the case of fermilam. This is the central region, so this is a mesonic state. One more. I don't want to go into the details of fits. I just want to stress that the importance of resonances compared to the smooth behavior. So we have smooth behavior in X, and we have resonances. The same is in the missing mass, and you can see it here. So the asymptotic is smooth. The behavior near 1 in X shows resonances. And how to describe these resonances? That was the main point of our activity that started in Calabria almost 10 years ago. And the answer comes from duality. The scattering amplitude, or a structure function, can be viewed either as a sum of resonances or a sum of Reg exchanges. Diagrammatically, with quark diagrams, it looks like this. And for missing masses, in the horizontal line, we have missing masses. We have the same picture, duality in missing mass, finite mass sum rules. For large masses, we have a smooth behavior, while at low missing masses, we have resonances. Everybody was concerned with smooth behavior, and maybe we were among the first to describe in that paper of 2003, describing the class data on deep inelastic scattering. This is the diagram of deep elastic scattering with resonances using the so-called Regiaist dual Breit-Wigner formula. So the scattering amplitude, or the total cross-section, the imaginary part of the scattering amplitude, total cross-section in the direct, here is the diagram for meson production, is a sum of Breit-Wigner-like resonance poles, here it is, and they are governed by nonlinear complex Regge trajectories in M square. In the direct channel variable, the missing mass, don't confuse it with T. So we have a T channel trajectory exchanged at small t, and we have an S channel trajectory ranging from the threshold up to 100 G square, that is 10 MeV, 100 if squared, and this trajectory is nonlinear complex function. And the goal, the problem is how to construct, how to use, how to insert this complex trajectory into the model. Now, a rather simple example is center production. So let's forget about the upper and higher vertices and concentrate on the popular subject of meson production in Pomeron scattering. If you will ask me, or better, I ask you how to describe the total cross-section of Pomeron scattering. Two Pomerons collide, and they produce a resonance. So here is our answer, the Regiaist Breit-Wigner formula. This is a pole term of this trajectory, but we now talking only about the central part. While the situation in reality is much more complicated, we have also external vertices, this and this. And we have calculated with Rainer Schicker and other co-authors, István Szonyi, this central part by using this formula, where alpha m square is a direct channel trajectory meson trajectory, producing mesons, for example, glue balls or oddballs. This is the simplest analytic model of a trajectory that combines, as I told, square root asymptotics with a square root threshold. These are simpler ones. For example, one can construct the linear part like this one, in the simplest way, add a square root or even a logarithm, but the simplest true answer is this one. The only problem is that the threshold as the value of S0 should correspond to the lightest, lowest threshold in the given channel. This is the outcome. The cross-section of fictive Pomeron scattering. Pomerons cannot be produced, so central production is called to be a gluon factory. Pomerons collide, producing meson states, among which are Fs and also glue balls or oddballs. Here is an example. One can calculate the width, the ratios of width. These states can be calculated, can be predicted, but only for the fictive process of Pomeron-Pomer scattering. Now, with Rainer, Istvan, and Sasha, we are thinking of calculating the whole diagram with external vertices included. So here again are the trajectories of the meson states. So you see the spin rises, and if the trajectory to have finite width, one has to have complex trajectories. Also, the masses can be predicted, I repeat, for the fictive Pomeron-Pomeron scattering, and I may ask people working in quantum field theory and quantum chromodynamics, how would you calculate the total cross-section of a glue ball produced in gluon-gluon or Pomeron-Pomeron scattering? Once we learn, if we know how to manage, how to work with the glue ball, one can do the same for the oddball or the Autore, which is much smaller, which contributes much smaller. So it is rather speculative. Here are the oddballs. They are barely visible in this plot. The same in this plot. Now, coming back to the whole diagram of single diffraction dissociation, we can calculate almost everything, and we did it for double diffraction with Kuprash, with in about between 2010 and 2015. Everything can be calculated, and it's shown here. For example, the integrated cross-section integration should be computed within definite limits. The dependence of missing mass, which is dramatic. One predicts resonances in the missing mass. By the way, these resonances were clearly seen at the Fermilab, but they are still under study at the CERN LHC. This is a plot for the distribution of the cross-section in two missing masses, M1 and M2. So now, open problems, and I come now to the discussion of these open problems. The main problem is to construct a model for the trajectory, complex trajectory that would be almost linear at small values of t, and asymptotically would behave like a square root. So this is an open problem. We are working on it. I've shown you a simple, very attractive, simple model of the trajectory that is not perfect, however. Now, if we do that, we should identify the mesons produced in the central regions. They can be F mesons, glue, and oddballs, and one has to identify them by mass and by quantum numbers. Now, heavy flavors. LHC may be interested in calculation and production, calculation of cross-section for heavy flavor production. This can be done by following the experience of in this at deep elastic scattering at Hera, where in gamma proton cross-section, heavy flavors were also produced, calculated, and compared with the data. Now, if we go down in energy, or if we consider not only one central system, but a multi-gap event, then the energy within the gap should be shared, and then secondary trajectories must be included. So this is also a technical problem that can be done. And of course, after we settle these details, one has to fit the data better to collect all the existing data that can be used in the fit. And then experimentalists will ask for Monte Carlo simulation. Glue balls were discussed, calculated in various papers independent of the Regge approach by Frank Close and Kirk. They can be found here. Now there are several more problems. For example, the cross-section of diffraction dissociation would rise too fast. It rises faster than unitarity allows. Dino Boulianus suggested to renormalize, which I don't think is very elegant, just to renormalize, that is to multiply the cross-section by a factor that will lower the rise of the cross-section. There are many other applications with nonlinear trajectories. The widths can be calculated, but I repeat, by this I want to stress the importance of knowing the nonlinear behavior of the trajectories. Now, before you start asking me, I want to flash once again. I want to flash you, go once more through the main points of the presentation. Yes. So I shall flash the main points of my presentation, and so that maybe you will better see the questions. So here are the diagrams in question. This is the simplest elastic one. This is an exponential one. This is a nearly linear trajectory exchange in the T channel. The first Main problem is passing from this elastic vertex to this one. So this is the first important challenge that I think we resolved it in 2003 in Calabria by replacing this unknown inelastic vertex with a structure function of deeply inelastic scattering, known, studied very well at Hera. So comparing with Hera, this is a vertical particle. The region is identified or compared with the photon. Both are vertical particles. So instead of photon-proton scattering at Hera, we use the photon-proton scattering known from Hera to Pomeron or region proton scattering, and we insert this knowledge in this diagram. And now the canonical formalism is shown here. This is the regio-behaved radiation of a regio exchange by the proton, initiated by Ingerman, Schlein, and Donachie. So this is a smooth function. Virtually, this is the total cross-section of region proton scattering, no resonances. And this is the machinery used by 99% of people working in this field. And I think the problem is that people cannot produce resonances with these standard formula. Everything is correct. Everything is here. Single, double, diffraction, dissociation, central diffraction, that is double Pomeron exchange. The problem is that in the curly brackets, we have smooth regio behavior, and we, with my authors, replace this smooth behavior by the resonance behaved structure function borrowed from Hera. As I repeat that the one problem is how to construct complex trajectories. Francesco Paccanoni liked very much this formal approach, which is not simple. That is to reconstruct the imaginary part of the trajectory by dispersion relations. Formally, this is rigorous, this is correct, technically not easy. So the working formula, the total cross-section for Pomeron proton scattering producing resonances, is the low energy, low missing mass, which is energy otherwise, behavior of the dual amplitude, which I call Reggeist Breit-Wigner formula. Summation is on the resonances, and the number of resonances is finite. Here is a very nice model for the trajectory. Apart from the problem of the threshold, as I noticed, we would like to have square root asymptotic behavior, but it's difficult to reconcile with the known values of this at the threshold. So this is the problem. Now, the Pomeron cross-section, rather easy. There are no gluons, no quantum chromodynamics here, but one can write a Breit-Wigner formula with complex trajectory, S-channel complex trajectory in M square with a finite number of spin values that can help to calculate resonance in a fictive Pomeron-Pomeron scattering process. Having those formulae splashed in the beginning, one can calculate in the same way, single diffraction, calculate the cross sections, double diffraction, central diffraction, and everything we wish to have. So this is the outcome of the formalism. And with Rainer Schicke, István Szanyi, and Sasha Korenok, we are now working on the calculation of these cross sections. First, I'm addressing also my co-authors. I can't meet them except for Sasha, who is living not far from Kiev in Chernigov now, north of Ukraine. Otherwise, with Sonia and Rainer, we have problems due to the quarantine. So first we have to collect the data and fit them to the formula that are now available. Choose the best value for the trajectory. So that's all, and I leave 10-15 minutes for questions and discussions. Thank you.
Thank you very much, Laszlo, for the nice presentation. I open the question session. So anyone is welcome.
Rainer, let me first ask Rainer. What do you think? You understand me very well, and also Sonny and Sasha Skorenok. But first, maybe Rainer has some comment or question. Do you hear me, Rainer?
Yeah. Yes, Laszlo, do you hear me?
Yeah. So
thank you for this presentation. Yes, I do have a few questions and remarks also.
Let me a short minute. So we have now the whole machinery, all details that we have to put them together and fit to the data, apart from the trajectory that still is to be disputed, and collect the data. As far as I know, there are no new data from the LHC for many years, for 5 years at least. I don't know, maybe Pogosyan has some collection of data, but you know better. So that's all. But please go on with your comments or questions.
Now, Laszlo, of course, as you know, I am an experimentalist, and of course, I see this with much interest because it opens the way to make measurements and to analyze them. You have addressed the issue of Monte Carlo generators and so on and so forth. Now, before I go, and there are many aspects there that are still open now, but let me start with another question. I take here the opportunity to ask you a question which I have never understood so far, but I think for you if you go to slide 4 here in this presentation.
Yeah. What's on the slide?
Number 4.
Yeah.
Now I see slide 8. Go back one slide.
Yeah.
Still, I think you went back to 8, but I would like to see slide 3 and 4, which is the parametrization of the imaginary part of the meson and baryon trajectory. Those two slides I would like to see again.
Before I find it, let me start answering you that you prefer the analytic approach, do you? While I like very much the simple model.
No, I like the model. No, I like, but there is a difference between the meson trajectory and the baryon trajectory, which I do not understand, and which actually limits
the threshold.
No, not the threshold. You have explained how the threshold comes about, so I understand, or I believe I understand the need to have these threshold terms in the meson trajectory. And actually, you know that I have redone those fits that you published 20 years ago and successfully. Now, in the parametrization of the baryon trajectory, you not only have a sum of thresholds, but in front of that sum, there is a power coefficient, s to the power delta.
Yes.
Where does that come from as compared to the meson trajectory? I think, it would be nice if we could see that. It was in slide 8.
I have to look. Slide 8.
Slide 8. Oh, not here. No, not here. You had after that well,
it's probably in the other file.
It's in the other file, but it's also stop. Here it is.
Okay, yeah.
So you see equation 1, imaginary part is s to the delta, s to the power delta, and then there is the sum. This is for the baryon trajectory. That power in front of the sum is not there in the meson trajectory.
Yeah. Yeah, I don't.
Do you have an easy explanation why?
I don't have an immediate explanation, so I have to look.
Or in other words, could you think, because that prefactor I believe makes the fit a little bit ugly, because if you do not have that power factor, if you just have the sum, and then you have a sum over the expansion coefficient Cn, then everything, this expansion is linear in the unknown parameters, okay? It's just a sum, it's linear. And if you have a fit that is linear in the fit parameters, then there are very standard matrix formulations, algorithms where you can make the fit. But that prefactor, that power factor, makes it very ugly because it doesn't work anymore, that those matrix, the matrix approach. So one has to take refuge to a different approach. So my question to you would be, do you have, because delta is an unknown, delta is not known a priori, right? So delta has to come out of the fit.
Yes.
Now, do you have an idea or a suggestions how that s to the delta could be replaced by something else?
Not at the moment, Rainer. I have to look at it again.
Okay, so that's something to think about. That factor gave me a lot of headache over the last few months and years, actually,
I see.
in terms of doing the fit.
Mm-hmm.
The other issue, more from an experimental side, if you had a plot where you had a schematic picture where if one goes above a certain mass, there are no resonance anymore.
Yes.
So let's say a proton excitation, a proton excitation of 50 GeV or 100 GeV, there's still, that can be produced with a certain cross section, with a certain probability. Now, that system exists. It's not bound. It's not consist of resonance. However, it hadronizes. It will hadronize. Okay.
Yes. Yeah.
And at the moment, at CERN within ALICE, we have plenty of discussions. How will a heavy ion experiment look like in 10 years? What is the need to have forward magnets, the coverage of forward detectors? So then my question to you is, if you have a proton diffractive excitation of 50 GeV, how does it hadronize? Does it hadronize into a few pions with plenty of momentum, or does it hadronize into many pions of low momenta? How is the hadronization process? So are there any models? Because from an experimental viewpoint, it makes a lot of difference whether out of those 50 GeVs, do you get, let's say, 3 pions with average 17 GeV momentum, or do you get 40 pions with very low PT? Because they will go in different parts of phase space where you have to put detectors. So my question, and also the question then is, what is coming out of that system? Is it only pions? Is it kaons? Can it be baryon, anti-baryon pairs? Can there be protons, antiprotons coming out of that 50 GeV excitation? So this would be a question to you, whether you could think of any approach, any models applying or being applied to the decay of that unbound proton excitation, where you say it's not a resonance, but it exists, you know, within this, you know, it has a certain cross-section to be produced.
So, so the answer is twofold. One is that the problem is related to the Hagedorn spectrum. You know what I mean. That was called whether the hadrons boil into a soup of quarks and gluons. That is, the resonances disappear. That is the question. Or they survive, just they become wider and lower. Or there is a phase transition. That's the question. In our case, when the trajectory stops and there is no higher value of the real part of the trajectory, this is the point of the phase transition. And there are no resonances beyond. So this first part of my answer. The second, what are the particular states in which the experimentalists are interested? The one has to consider a specific particular vertex, proton region vertex. And the region may be a Pomeron, the simplest case, or plus secondary regions, F and omega and so on. And the product will depend on the exchange and on the energy. So this is this can be calculated in each particular case. That's the answer. Okay? Yeah.
Okay. Anya, do you have further questions?
István Szanyi, do you hear me?
Yes, I hear you.
I'm curious of you are a newcomer in this subject. What is your feeling? And be open and ask what is not clear for you, if anything.
Okay, thank you for your presentation. I think I understand the basics. I had more questions on the details, not on the basics, on the parameters and so on. What were the exact formulas which were used for the calculations? So I think we can discuss it in email later, because this is for the details, not for the basics.
Okay.
Laszlo, I have a question for you. In one of the slides, which I didn't take note of, you showed a fit and compared with the experimental data. I think it was for central exclusive production, and groubles were in that plot. It was a plot with several resonances, and then some of them were attributed to groubles.
For example,
yes, just this one, yes. Somewhere these GB means groubles, and they are located at some definite place, so at some definite value of the mass. So my question is, are these experimental values? Are there established values for the mass of groubles? Second question. Yes.
Yeah. So first of all, that this curve, the heavy curve, results from the sum of various components that come from various exchanges. Better to say various trajectories. Now about yeah, the experimental
Laszlo, we
data.
lost you for some
Yeah,
seconds.
yeah.
Laszlo,
Now,
can you repeat, please, because we lost the most part of your answer.
Yeah, so the first part of my answer is that in this curve, now you hear me?
Yes, yes.
We have this heavy curve is a sum of various colored curves that correspond to various trajectories. They sum up, giving this curve, where somewhere the glue ball can dominate, and in other places the normal F mesons dominate. Now about the data, experimentally, and maybe Rainer can say more, this is what we have, not too much, I think. So it's not easy to identify, or even less.
So this is supposed to be a signal for a glue ball?
Yes, that can be mixed.
So
yes, it can be, it's a candidate for the glue ball that can be interpreted as being mixed with ordinary methods. That's the problem, that they are mixed.
Okay. Then my second part of my question is: did you input in your fit the value of these global masses, or they came out of your procedure? I mean, did you predict these global masses, or somehow you had to input in your model?
The only input is in the trajectories. The secondary trajectories, for example, F, and this is related to Rainer's question, and the trajectory of the glue ball. So the trajectories are the only dynamical inputs.
Okay, so you use the information about mass of glue balls only through their trajectory.
Yes, yes.
And then you got these peaks just at the right place.
Yeah. Now, let's come back, which is intriguing for us. Or we.
Sorry, Laszlo, can I add something here? This is this glue ball histogram you showed. I think this is out of our first publication.
Yes.
I remember it depended a little bit because we had a parametrization with 3 coefficients, 3 unknown, and we fitted those coefficients that we get the intercept, we get the slope right, and we had a heavy threshold, a second threshold at 3.5 GeV.
Yes.
And then the position of the masses of the glue balls is given.
Yes, that's the most disputable. Now, coming back to the comparison with the data, all this concerns a fictive Pomeron scattering, while the data can be related only to proton scattering. So we did not, Rainer, you remember how much we discussed, we did not include the so-called external vertices. You see? That we have calculated only Pomeron.
That is correct. That is still to come. This will be part 3 of this Fiore Jenkovszky Schicker trilogy.
That now I think that the main message of my seminar, that now we have all the formula. We have problems with the trajectory. This is the main problem, which is difficult by itself, the construction of nonlinear trajectories. But for the cross sections, we have now complete the whole set of formula with single, double, and central diffraction.
Okay, thank you. Some further questions, comments?
Laszlo, let me ask another question here. This is a very good starting point. You remember here that we take the sum of different trajectories, and then as we go to high masses, this is only shown up to 7 GeV. As we go to high masses, the background will dominate, which was given as, which we took here as a certain parametrization, 1 plus some logarithm. Now, on the other hand, you showed can this be connected with this, with the one slide where you had cross sections following the Dinos approach, Gulianos, Chisielski. You had one slide where you had cross sections for single diffractive, double diffractive, but also as in central diffractive.
So here are the main formula. Here they are.
Here, yes.
Everything is here. And what
yes.
I repeat, that is maybe the most important in whole my talk, that this is canonical, accepted by everybody, started by Ingelman and Schlein, and supported by Lanzhoff and Gulianos. They're transparent, easy, and accepted completely, except one thing. They do not produce resonance. These are smooth cross-sections, asymptotic, rigid behaved cross-section. In this case, it's Pomeroy, epsilon. And
but somehow, if you take the limit there, the last line, double Pomeroy exchange, that makes a central state.
The same.
The asymptotics to large masses must be is hidden where? Is this the S prime? The S prime. The S prime.
The same. Asymptotic, hopelessly as a smooth asymptotic behavior with no hint to any resonance. That's the point. So everybody, I have no idea how people will try to reconstruct, to make resonances at the LHC, to predict resonances, either in baryonic or mesonic, here or here. So that's the point. We instead replace this smooth behavior with the resonance model, Regis-Breit-Wigner, I call it this way, of 2003, when for the first time we have described very nicely the class JLab resonance data in the structure function. And I repeat that we identify the deep inelastic photon proton structure function, be it at DAISY or JLab, with the region proton cross-section, identifying the region virtual particle with the photon, virtual photon. And in this way, from this smooth behavior, here we insert resonance behavior. That's the main point. The problem remains, the major problem, how to construct a reasonable nonlinear complex trajectory that is a problem by itself, independent of this activity. That's what I wanted to say. And now we have this set of formula in early papers with Kuprash, we did this part, single and double diffraction, without central. Now with you recently, we did center production, but only for the fictive Pomeroy cross-section without involving the external lines. So we did this one, this piece, without the external vertices and energy. The energy comes in like a liquid, like water, and then it is partitioned by various channels, here, here, and here. So that's the dynamics. We have calculated this one with resonances, and now I'm very curious that what will happen, will change, if we include also these two, also the others. So there are many combinations, and they all are coherent and they should work.
Okay, Laszlo, thank you. There are,
Thank you.
it seems that I can't see any more questions. So I think we can, it's time to say goodbye. Thank you very much again. So we virtually clap to your presentation.
Thank you. Thank you.
And okay, hope to see you soon somewhere, somehow.
Yeah. Yes. Yes.
And okay, goodbye everybody.
Bye. Thank you. Bye.
Bye-bye.
Bye-bye.
Bye.
Bye.
Bye. Bye.
Bye.